All right, sounds like some good discussions. Anybody want to volunteer one of these where there was a discrepancy of some sort? Something that you didn't agree on. Maybe you agreed on the same molecule, but you had a different explanation or a different reasoning. Anybody have that situation? You all said the same thing for everything?
We're close.
You're close? Okay. Anybody want to? You don't have to even say names. You can just say one person thought this, but the other person thought this. And then I'll have no idea who said what. I'm curious about the discussion that took place. All right, how about for A? What was the nature of your discussion for A? Strength of bonds. How so?
So they both have the dispersion. I could be wrong, but isn't like a higher vapor pressure? Does that come with like stronger bonds?
What do you think? So you read? When you say bonds, what do you mean bonds?
Like the bond between like how like carbon, hydrogen, and then how chlorine fits in there too.
Okay, so if that said, then it's the stronger bonds determining the vapor pressure is your idea. So that means that when something vaporizes, those bonds break. And so if, let's say, methane, which is that first molecule, when methane vaporizes, what do you have in the vapor? Carbon and hydrogen individually, no longer bonded together. Maybe? Anybody disagree? Agree? No? Everybody's good with that? Not good with that? Yeah.
Isn't it that bonds they vaporize because they just change speed?
Yeah. 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 So, sorry. But no, but it's important that we went there because that's a really, really common thing. We talked about that last week, that's kind of what we usually think about. And that's how most people think about these things, that the strength of the bonds determines the vapor pressure or the boiling point. But we know that evaporation is not a chemical process, it's a physical process. So you're not actually changing the compound. When you boil water and make steam, you haven't made hydrogen and oxygen, you've just made water vapor. So it's not the bonds themselves that break, it's the molecules that separate from each other. So it's the forces between molecules that are breaking. So that said, what's the difference between the methane, which is CH4, and chloromethane, CH3Cl? Did anybody come up with some other explanation besides the bond strength? Yeah. No?
You said the less number of particles, the higher the vapor pressure.
The fewer number of particles. What do you mean?
And the fewer number of particles. The fewer particles.
So the higher the particle mass.
Okay, yes. So the bigger the mass, the word particle confused me a little bit, but okay. So the bigger the mass, the higher the vapor pressure. Therefore, CH3Cl would have a higher vapor pressure, or lower vapor pressure. Okay, what do you think about that? Is this effect controlled primarily by mass? Yeah, so in this case, that's a true statement, by the way, about the mass thing. It's true that a higher mass leads to a lower vapor pressure because bigger things can stick together. But we can only use that to judge things like this when we have the same type of forces. Remember our hierarchy of forces from last time? What were the very weakest forces? Dispersion forces, and then dipole forces, And then the strongest, besides the ion ones, with the strongest non-ionic forces, are hydrogen bonding. So within each category, we look at mass. But if we have different categories, then we have to look at that first. All right, a very heavy nonpolar molecule is still going to have a higher vapor pressure than a very light hydrogen bond molecule like water. So when we're looking across categories, the mass thing doesn't always work itself out. In this case, we have to think about the strongest intermolecular forces at work in each of the compounds. CH4 is totally nonpolar, so we've just got dispersion forces. CH3Cl is polar, so it's going to have a dipole moment. The difference in electronegativity between carbon and chlorine is significant, so we have a polar bond there, an overall polar molecule, so now you have dipole forces. So if you're weighing dipole forces against dispersion forces in a similarly sized molecule, the dipole forces are going to win out, are going to be stronger. So the methane should have the higher vapor pressure, more vapor, more volatile, and chloromethane should have the lower vapor pressure because the molecules are held together more tightly. All right, what about B? We have this larger molecule, which is called propanol, versus the smaller molecule called methanol. How do you think about the vapor pressure with these two? So why does that work in this case? They're made of the same molecules, yeah, or they have the same types of forces. These both have OH. These are both up in that hydrogen bonding category. So now we can weigh them based on size because we know they have the same types of forces. So that means that the larger one is going to have stronger forces between molecules. That one's going to have the lower vapor pressure. Remember, the lower vapor pressure, the less volatile, the less vapor on top, the more it's locked into the solution. The higher vapor pressure means the molecules aren't locked together as much as in the liquid state, and more of them can form the gas state. All right, and then finally we've got CH3OH, which is methanol, versus H2CO, which is acetone. So for this one, you probably want to make a Lewis structure of that, at least that second molecule, if not both of them, to make sure, because they're both made of the same types of atoms, CH and O. So we want to know, the first question is always, what types of intermolecular forces are going on here? The only way we could tell that is if we knew the structures of each of them. So did anybody come up with a structure for that second one? Oh, that's not acetone, by the way, that's formaldehyde, sorry. Anybody come up with a structure for that? Yeah, it'll look like this. So is that going to be polar? Will that molecule have a dipole moment? Shaking your head? No? Or you just don't? Yeah? Why? No, yes. Yeah, oxygen is a higher electronegativity than carbon, so that's a polar bond. Carbon and hydrogen have roughly the same electronegativity, so there's nothing else to offset that. So there is an overall dipole moment. Can this molecule do hydrogen bonding? No, because there's no OH bond. That's why it's important to get that structure. If you just looked at the formula, it might not be totally clear that there's no OH bond there, so we have to be careful of that. So that said, which of these is going to have the higher vapor pressure? That one. Why? Yep. Right. It doesn't have as strong of intermolecular forces because it can't do that hydrogen bonding. so it can more easily form that vapor, and it's going to have higher vapor pressure. The molecules aren't held as tightly together. All right, sound good with those? So last time we talked about ranking boiling points, then we ranked vapor pressure, and now we're going to look at solubility, which is something else that we can figure out with intermolecular forces, and this is something that will come in chapter 12 as well. Which of these forms a homogeneous solution and which doesn't? How are you going to make that distinction? How can you make that distinction? How could you use intermolecular forces to determine whether two substances will mix or not? Mix homogeneous, make a homogeneous solution or stay separated in a heterogeneous mixture. Yeah, they're going to need similar intermolecular forces. Remember these pictures that we looked at last time? Okay, well, we see them here for the ions, but this could be true for other molecules also. When something goes into solution, and we'll see more about this in the next chapter, the solvent molecules are surrounding the solute molecules. And so for that to happen, they have to have the same types of forces so they can interact with each other. So what that question is really asking is, can molecules of one of those things interact with molecules of the other? Do they have the same types of forces? Non-polar molecules can't interact well with polar molecules because the polar molecules would rather stick together with themselves and the non-polars would rather stick together with themselves than mix up. When you introduce that polarity, now you can have this kind of solvent interactions. So let's look at that again. CCl4, which is called carbon tetrachloride, sorry. We used to use that a lot as a solvent. It's a carcinogen, so we kind of don't now when we don't have to. But carbon tetrachloride and water. What do you think? Will those form a homogeneous solution, or will they separate into separate components?
They'll separate
Why?
because water is polar and CCl4 is not polar.
Yeah, water is polar, CCl4 is nonpolar. Now we know a carbon-chlorine bond can be polar, but when there's 4 of them around in a tetrahedron, all those dipoles are going to cancel each other out. You have something that's overall nonpolar. Now I would challenge you to go a little bit further with that, rather than just saying polar and nonpolar, although that's true, to think more deeply about the forces, which I know you all know about, that water has this hydrogen bond network. And in order for water to mix with something else, that something else is going to have to fit within that hydrogen bond network and break up those nice hydrogen-oxygen interactions that we know are so strong. So if it's going to do that, it's going to need to also be polar. Something like carbon tetrachloride will not break into that network because it can't line up with any of the negative or positive parts of the water. And so those things will stay separate. What about KCl and water? B. Are those going to mix or not? Who says mix? Who says not mix? All right. No, not a lot of votes here. What's KCl? Okay. What does it look like? what state is it in usually? It's a solid. It's a salt, like sodium chloride, potassium chloride. So this is saying, does potassium chloride dissolve in water? Now you could look it up on a solubility table, but I think we can figure it out based on what we know about these forces. So what do you think? Would you call KCl polar? Maybe. It's a little bit of a not exactly a right word in this case because KCl is an ionic compound. It forms ions. And that word polar really refers to covalent bonds. Polar covalent is kind of that middle ground between covalent and ionic. And so when we say that that's polar, that's not really exactly right. Really, we should just say it's ionic. But being ionic, it has positive and negative charges. So we would expect that to break up into ions and be surrounded by water molecules, just like those pictures of sodium and chloride I showed you before. So those would absolutely form a homogeneous solution. If that's true, then why are there some compounds that are not soluble? Why are there ionic compounds that are not soluble in water? Anybody remember any of the insoluble salts from that table? Let's say a hydroxide or something, right? Yeah, like a hydroxide, like copper hydroxide or whatever. Here is an ionic compound made of a charged ion and a hydroxide ion, which is almost like water itself. So why might a hydroxide ionic compound not be soluble in water, even though it seems like it should have the same types of intermolecular forces? What else is going on there? Why are some of those compounds not soluble, even though they are ions, even though they are charged? No ideas? It's quiet today. You guys have a big weekend? Just ready to be done with this class?
Hydroxide is really similar to the similar to the hydrogen oxygen bonds from those between the molecules.
Yeah.
So it isn't strong enough to break the bonds that the molecules already have in water compared to.
Okay, so that's interesting. So there wouldn't be enough of a difference, you're saying, for them to try to want something new?
Yeah.
Okay, maybe. But of course, there are hydroxides that are soluble, like sodium hydroxide. So how do you if we're basing our solubility decisions on intermolecular forces, how do you justify that something like sodium hydroxide is soluble, but something like copper hydroxide or calcium hydroxide is not? What else goes on in those solubility rules besides intermolecular forces? Nobody? Just awkward silence? All right. Well, we have to think a little bit about how solutions are built, and that gets us into the next chapter. What has to happen for a molecule or an ionic compound to go into solution, like KCl or like one of these hydroxides we're talking about? It has to break the ions apart in their solid state and then recombine them in solution with solvent molecules all around them. So do you remember this idea of lattice energy? This was on the last exam. Remind me of what that is, what that talks about, or what that applies to. It's lattice energy. You don't have to give me like an official definition, just what does it refer to? What is it about?
The energy associated with forming like a lattice structure. Yeah, the energy associated with forming a solid structure. So packing the ions in solid, that releases some energy because they're more stable when they're packed together like that. So when you make a solution, you have to break that up. You have to put in that lattice energy. But then you get back energy from the solvent-solute interactions too, from making those solvent molecules surround those ions. So it's the balance of those two. If you get a net advantage from making that solvated ion, that ion with the solvent all around it, then you're going to make something soluble. If they'd be happier just staying in their lattice by themselves because they have a really high lattice energy, then you're probably going to keep them in those lattices. So, so it's not exactly just this idea of does it have the same kind of forces, it's also thinking about the lattice energy. Okay. So that said, oh, there was one other thing before we move on to solutions. One other thing that we should look at, because we kind of just did this at the end last time, the other types of questions, I mean, I would encourage you to go through all of these problems, but let's do a phase diagram problem. I'm going to copy these in a couple parts so we can see them both. All right, so here's a phase diagram, not to scale, just a phase diagram with some points on there. And the question is, identify sort of what's going on. Identify the phases that are present. If you are at this point in temperature and pressure with this particular substance, whatever it is, what would you have? So if you are in, let's say, A. Well, let's start with A. So we have a sample at this particular pressure and this particular temperature. What type of a phase do we have? It's going to be a solid, right? The highest pressure, lowest temperature phase of a substance is generally going to be a solid. So that's going to be all solid. All right, what about B? See B right up here? What's that one going to be? Liquid. That's that middle phase. You can usually tell a liquid because it's in between the solid and the gas phase. At very high pressures, you're going to usually have a solid. At very low pressures, you're going to have a gas. Somewhere in the middle there, you can have a liquid, usually at slightly elevated temperature. All right, what about C? I heard it, gas. Yeah, C is going to be our gas. All right, so now once we've determined that, we can say, here's the solid region. Here's the liquid region. Here's the gas. So now we can get into some of these trickier spots. What's D? Way up here in the corner. If you are beyond liquid or gas in temperature and pressure, what do we call that? Sounds like something that would be in a superhero movie or something to me. Like somebody's secret weapons. That's actually not that exciting. Anybody know what it's called? Kind of. It's a supercritical fluid. Sounds important, right? Sounds like some kind of super weapon or something. Get the supercritical fluid and aim it at the, I don't know, ship, bad guys. I haven't been to a movie in a long time, so I don't know. Yeah, so we didn't really talk about what a supercritical fluid is. It is kind of weird like that. I don't think I have a picture of it on here anymore. There's a nice picture in the book on page. .508. So we'll just kind of look at this.
here we're looking at a window into a pressurized chamber of water. Or is this CO2? This might be CO2. It doesn't say. So you can usually see when you have a sample of something, of a liquid, you can see a line that separates the liquid from the gas above it. We talked about how every liquid has a vapor pressure, but if you look at water like this, you can see the top of it. You can see the point where the liquid stops and the vapor starts. So as you boil it, here now it's boiling, starting to boil, and now at the boiling point. Now at the boiling point of a liquid, you have both the liquid and the gas phase. But remember, the boiling point is when the vapor pressure is the same as atmospheric pressure. So you have both things there, but you can still see the difference between the two. You can see the vapor on top and the liquid on the bottom. Once you pass that critical point, that little point up in the corner, you get a supercritical fluid, which is the thing on the right, which is both a liquid and a gas at the same time. It's a totally different state of matter. And it has some properties of a liquid, like that it can flow and that it can be used as a solvent. It has some properties of a gas. It's compressible like a gas. So it's not really one or the other. It's this new thing, and that's a supercritical fluid. Supercritical fluids are interesting because they have different properties from either the liquid or the gas of whatever thing they come from. For instance, supercritical carbon dioxide is an important solvent because it has different properties from either liquid, solid, or gas carbon dioxide. And one of the big uses of supercritical CO2 is caffeine extraction from things like coffee and tea. If you have decaffeinated coffee or decaffeinated things like that, what they'll do is soak the coffee beans in supercritical CO2 fluid. It turns out, just kind of because it happens that at a particular temperature and pressure, you can tune the solubility of supercritical CO2 so that it dissolves caffeine really, really well and doesn't dissolve the other stuff in the coffee really that well. So they find that exact point, they put it in there, it extracts the caffeine, they take out the beans, and then all you have to do is let the pressure come back to normal, the CO2 evaporates, and you're left with your pure caffeine. So you've taken it out and you haven't introduced any more chemicals into the coffee because the CO2 will just evaporate when it's done. So they're very clean. You talk about things like green chemistry or green solvents, things that are good for the environment. This is an example of that, where you don't have to use any hydrocarbons, you don't have to use any poisonous solvents. There's really no waste because you can reuse that CO2 as a solvent again after you extract the caffeine out of it. So that's one of the uses for these supercritical fluids. But that's where you'll find them, up in this high right corner of this phase diagram. All right, so what have we got in some of these other ones then? What's at point E? What does it mean that we're right on that line? What does it mean to be right on the line in the phase diagram? Yeah, that's right at the transition. So that means that we'll have whatever this stuff is, we'll have the solid and the liquid at the same time. And that's what we call the melting point. So that's when you have both solid and liquid existing at the same time. Depending on how much energy is there, you'll eventually go into one state or the other. So then what's F? Right, liquid and gas. If you had a sample exactly at that temperature and pressure, you would expect to see both a liquid and a gas. And then finally, G. What do we call that point G? The intersection of all of them. There's a name for it. Right, it's called the triple point. Super creative name. The triple point, you have all three phases present at the same time. So you'll have solid, liquid, and gas existing simultaneously. All right, and that's how we read a phase diagram. Questions about that? All right, back to these problems. Oops. There's one other type of phase diagram that we should look at. And then I'm going to show you some to scale phase diagrams, and we can see why they're kind of messed up. This one here, this is a phase diagram for sulfur. Sulfur not only can melt and boil and all the stuff like whatever, but it also has two solid states. One of them is called rhombic and one of them is called monoclinic. And you don't need to know what those mean, because we didn't really get into that structures of solids. But it doesn't matter how many different phases there are here, a phase diagram tells you the same thing. So if we wanted to look at phase transitions between the rhombic and the monoclinic forms or structures of sulfur, we would look at this line and we would say, okay, well, right here you'd have both. On this side you'd be rhombic. On this side you'd have monoclinic. So I guess my main point is just don't be scared by that. There can be very complex phase diagrams, but they still say the same thing. Here's another example. Here is a not to scale phase diagram of water. If you look way up in the upper part of water's phase diagram, at super high pressures, you get different forms of ice. There's not just one ice structure. There are different ice structures. And if we look down, like deep in the Antarctic ice and stuff like that, we'll see these different things. And then certainly in space, we see a lot of these different ice structures. So there are different ice phases that we can make depending on where we are in the phase diagram. And you can see that way up here in these pressures, oh, I can't write on this one, I forgot, that we can transition from one ice to another. So ice 7 to ice 6 to ice 5 as we go down in pressure and temperature. And then those can also themselves melt into water. Of course, the standard ice that we know is just called ice 1. So don't be, yeah.
Where is ice 4?
Where is ice 4? Not on this phase diagram. I don't know. Good question. Let's look it up. Ice skating, yeah. Let's see if we can find a good like. Here's kind of a backwards one. All right, so here's our pressure increasing. And now we're not even seeing the gas because we're at such low temperature and relatively high pressures here. I don't see 4 in that one either. Maybe there is no ice 4. Maybe. Go discover it. See if you can find it. So there's some of the different ones. It could be that it could be one of those things like it was discovered, but then they realized it was actually the same as another one. And so it ended up being. Oh, okay, here's the example. Ice 4, a metastable. Metastable means only transiently stable. Like when you make it, it automatically goes to something else. It can be formed by heating high-density amorphous ice slowly at this particular pressure. It doesn't form easily without a nucleating agent. That means that you need some ice 4 already to help it to become ice 4 in that way. So it doesn't really exist, sounds like, naturally on its own. It's something that just happens transiently. But there's all the different ices. There's actually a book about this called Cat's Cradles. Have you ever read that? By Kurt Vonnegut. One of the plots of the book is that sort of like I don't remember, it's been a long time, but something like a terrorist group finds a new form of ice that makes all other water freeze as soon as it comes in contact with it. And so they're using that to like get rid of all the water on Earth. That's part of the threat. I think, is that am I thinking of the right book? Or is it the one, is it Mother Night? One of his books. Ice 9, yeah. What book is that in? Cat's Cradle, right. It's supposedly more stable than common ice, and it like solidifies all the ice. Anyway, different state. There is actually a real Einstein that I don't think was discovered at that time. Okay, so that's phase diagrams. Main things then you need to know from chapter 11, things that you should be able to do. Ranking boiling points based on intermolecular forces, describing those intermolecular forces, understanding those intermolecular forces, hydrogen bonding, dipole interactions, dispersion forces, what are they, where do they come from, and then how can you use them to rank boiling points, vapor pressures, pretty much anything any property that involves things sticking together, solubility, viscosity, that sort of thing. And there's lots and lots of practice with that in the problems at the end of chapter 11. The stuff about solid state formulas that you see in the second half of chapter 11, we'll skip over that for now. All right, let's talk about solutions. Some terms you should know. Some basic terms you should know. I'm not going to go again through all this stuff, but a few things that I think are important that will come up for you, at least, if not in the exam, maybe in life. And then we'll talk about an interesting application of this. So firstly, concentration is kind of a messy problem in that there are a lot of ways to measure concentration, and there are various situations where one works better than another. We've only really dealt with one measure of concentration, which is what? Molarity. Molarity is great because it gives you a concentration in terms of moles. So when you're using a solution in a chemical reaction, that really simplifies your calculations because you've automatically got your moles and you can calculate all this other stuff. But out in the real world, the non-chemistry world, molarity is not usually a common concentration. And the reason is because it's harder to make solutions with a particular molarity. You have to measure things out much more carefully, and you have to do some extra calculation. So most of what you'll see in percents out in non-chemistry environments is percent concentrations. Has anybody ever seen that? Like if you look at a bottle of something and it says whatever percent, if you buy I don't know, some kind of solvent in a hardware store. You can buy hydrochloric acid in the hardware store. It's called muriatic acid. And that will say it's a particular percent concentration of hydrochloric acid. I don't remember what the percent is. But those kinds of things. Because it's easy to make a mass percent or a volume percent. You just measure out so much of this, you measure out so much of this, you put them together. The tricky thing about percent concentration is that there are different percent concentrations. And you have to keep them straight. So first, we've got mass percent. Another way that this is often described or written is percent M over M. This one's just like molarity in that it's solute over solvent or over solution, but it's all masses. So if you've got 10 grams of solute in a 100-gram solution, that would be a 10% by mass solution. This is a nice measurement because it's completely general and it doesn't care what kind of phases or anything you have. So you can have mass percent of gases. You can talk about the mass percent of oxygen and air. You can talk about mass percent of liquids together, liquid and solid. You can talk about solid solutions in mass percent. When you talk about alloys, that kind of thing, those are often given in mass percent. So it's very general. But it also requires that you have a scale or a balance to measure all of your stuff in mass. So sometimes it's not always convenient. But that's one that you'll see, that you may see come up. I don't know why I didn't put the others. Probably I'm skipping a bunch of stuff. But let me make another page because I want to show you a couple other concentrations that you should know too. So let's put these all together. So percent mass by mass percent is mass of solute over mass of solution times 100%.
There's also volume percent. If you have 10 milliliters of this liquid in 100 milliliters of solution, you have a 10% solution, 10% by volume. And we should probably put that in here too. This one's called percent by mass. And this one's called percent by volume. And these are totally different measurements. If something is a particular percent by mass, it's going to have a different percent by volume. It's going to have a different molarity. Those are not interchangeable. And if you get those wrong, if you don't get them straight, you cause some problems. And the main place this causes problems is in health professions. Health professions, has anybody ever worked in like pharmacy or hospitals or anything like that? Maybe. They have all kinds of different measurements for everything, because it all comes from what somebody decided to measure something in, 100 years ago, and now they still measure it in that. So some medications are in grams, some are in milliliters, some are percent by mass, some are percent by volume, some are in molarity. If you look at an IV bag, those fluid bags that you give solution to somebody, they'll actually have different ions in different concentrations in the same bag. So one thing, glucose will be measured in molarity, but then the KCl will be measured in percent by mass or something like that. So sometimes those just mix up and get all confusing. And if you're trying to do specific calculations to figure out what somebody needs, you have to keep this stuff straight. And it's not hard to convert between them. We all know how to convert masses to moles and that kind of stuff now. But it's just something you have to do. And you have to make sure to realize that these are not the same thing. That if somebody says, hey, give this person 10 milliliters of 1 molar, whatever, it's not the same as 10% of 1 molar, 10 milliliters of 1% something. So keeping that stuff straight is really important. The third percent thing that we need to know is percent mass by volume. And this is the mass of solute over 100 milliliters of solution. Percent mass to volume. And even though that one looks a little confusing, that's actually probably the most common, because that's the easiest one to measure. You take 5 grams of this, you put it in solution with 100 milliliters of, fill it up to 100 milliliters, and you've got your thing. You don't have to convert to any moles, anything like that. You're just done. So those three will come up a bit. Yeah. I'm trying to think if I missed anything important. Those are 3 concentrations. So one of the things we're going to do after we go through all this is practice converting between these different modes of concentration. But before we do that, we have to talk about a couple more that are a little bit weirder. Mole fraction we already know about, right? We talked about that with gases. Moles of 1 divided by the total moles. So that we can deal with. The one that most people forget probably the most is something called molality. Not molarity, but molality. Molality is a measure of moles versus mass. So molarity was moles per volume of solution. Molality is moles of solute per kilogram of solvent. So note, not solution, but solvent. So you take however many moles of this and you put it in a kilogram of water. And that's the molality. So why would you need that? The only time, the answer is you don't. But I mean, it's a thing. I mean, it is a measurement, and it comes up in some industries and some. You'll see it in the health careers as well, and things like, especially in pharmacy. We don't see it that much in chemistry, so I can't tell you a whole lot about it. the main use of it is that you don't have to deal with density changes. When solutions change temperature, they change density. So if you had a particular molarity and then you change its temperature, you've actually changed the concentration because the density has changed a little bit. You have less than you did because volume changes with temperature. Does that, you understand what I'm saying? So the mass will stay the same over changes in temperature, but volume changes because of the density changes. It doesn't change a whole lot, but it does change. So if you're doing really careful measurements and you need to compare things across different temperatures, this is a better measure because the kilograms of solvent isn't going to change. So in reality, you'd probably use mass percent or something because it's easier to deal with, but this is out there as well. I don't think you need to, I don't know. I don't think you'll come across it. Maybe. All right. So let's practice this. A solution is prepared by mixing a gram of ethanol with 100 grams of water to give a final volume of 101 milliliters. Calculate the molarity, mass percent, mole fraction, and molality of ethanol in the solution. Sound like fun?
No.
All right, we'll do it quick, and it'll be like tearing off a Band-Aid, and it'll be done with it.
Okay.
All right, everybody give this a try. So you got to try to keep these things straight as, you just have to plug into the equation. The only tricky thing about this is keeping straight what quantities you need, what things you need. Anybody got numbers for these? Anybody find the number of moles of ethanol? That's going to help our calculation here. How many moles is 1 gram of ethanol?
I have to entertain myself while you're doing all these annoying calculations. Anybody find some numbers yet? What? 0.2 moles? 0.02 moles? You guys are getting a little lazy with your significant figures. Is it just 0.02 or? 0.022. 0.17. All right, we'll stick with that. Okay, so let's make an expression for these, and then we'll look at the calculation. Molarity is going to be moles over volume of solution. So that's going to be our moles over 0.101 liters. Yeah? Great. And what does that come out to? Okay, and we would say that that is 0.215 molar. That's how we would report it. All right, what about the percent by mass? So this is going to be our grams of ethanol divided by 101 grams of solution. No, it should be just less than 1, or just less than 0.99%. Yeah. Okay. What about the mole fraction? So that's going to be our moles of the solute divided by the moles of that added to the moles of water. How many moles is 100 grams of water? What? 5.55 moles. And the thing to remember with these is just to make sure you add up both moles, because it's moles of both. So that whatever that comes out to. Okay. And then finally, the molal, that's going to be moles, 0.0217, divided by kilograms of solvent. So that's 0.100 kilograms of water. So that's 0.217. And the unit for molality is molal. So where molarity is molar, molality is molal. You'll notice those numbers are all different, some of them far more so than others. But they are different measurements, so we just have to make sure to keep them straight. And then the final one we look at, which only really applies to acids and bases, is normality. Has anybody ever heard of this? When you're normal. It's when you're normal. Yeah, it has to do with equivalence of acids. So it works like molarity, but if you have more than one hydrogen per acid molecule, then you multiply that to get the normality. So it's kind of like, you remember when we did all that acid-base titration stuff that you so enjoyed, and we could you had to set up the balanced equations because sometimes you'd have to multiply by 2, something like that, to get the right moles to work out. Normality attempts to account for that. So like if you have something like HCl, molarity is going to equal the normality because there's only one hydrogen there. But if you have H2SO4, the normality is double the molarity because there's 2 hydrogens per acid molecule. The reason for doing that is because when we work with an acid, we often care more about how about it acting as an acid, and with a strong acid, it's all dissociated in solution. So you just have hydrogen ions in solution. So if you have 2 molar sulfuric acid and 2 molar hydrochloric acid,
that 2 molar sulfuric acid is actually going to be twice as strong in terms of how many hydrogen ions are in solution. So that way, normality kind of is more of a leveler. If you care more just about the absolute strength of the acid, then normality is going to tell you that. But it's a little antiquated. You don't see it really as much anymore. So I don't think we need to worry too much about it. It's kind of one of those things I feel like it's rare enough that if it came up, you could look it up and be like, oh, okay, that's what that is. But it's not necessarily something you need to know off the top of your head all the time. I don't know, maybe you do. You could just know it for fun, tell people at parties. Yeah. I would think probably not. Maybe. It's a possibility, but I mean, if I were writing the exam, I would think it would be kind of a waste of a question to have that on there because, like I say, it's not something that comes up a lot. Doesn't mean it can't be there. I think the more important things are what we're going to get into now. The qualitative effects of solutions. That is, how do we talk about what's happening to solutions in a more general way? We talked about structure effects, polar versus nonpolar, that kind of stuff. There's also pressure effects. Have you ever seen this happen? Sometimes some kinds of drinks are carbonated and they're stored in cans. Anybody?
No.
This is new information. So you open the can and it kind of goes and the gas escapes. And what happens if you leave pop out for a while? It goes flat. So the carbon dioxide molecules escape out of that pressure. And another way to talk about that is by looking at how pressure affects solubility. We can say that under that high pressure, there is more carbon dioxide dissolved in the solution. And under the low pressure, it can come out and it can be released. All right, and that's kind of given by what's called Henry's law, which is just saying that the concentration is inversely proportional to the pressure. So the pressure of the gaseous solute above the solution. If you increase that partial pressure, you're going to increase. If you increase the pressure of the gaseous solute, meaning there's more gas on top, you're going to decrease the solubility. Yeah.
Which concentration should we use for?
It doesn't matter because we're not going to solve it because of K, a constant characteristic of a particular solution. So you actually need to know different constants for different solutions. There's not like a general rule with a general constant like R, like there is for gases. So the constant changes so that it's not really a practical calculation. We mostly just use the equation as a way to talk about how these things are balanced. And then something we really encounter a lot is temperature effects on aqueous solution. And one thing I want you to be able to do here is explain these temperature effects rather than just saying, here is the effect. So usually, when you heat water, more of a solid will dissolve. Has anybody ever done this? Like dissolve sugar in water or something, you need to heat it up to get it to dissolve, or salt in water. That's usually the case. Not always the case, but it's usually the case. So what you're doing here, let's look at a little picture of what exactly is happening kind of at the molecular level of making a solution. So first, the solid sodium chloride, which is the green and purple thing, is dropped into the liquid water. All right. And now at the molecular level, what's happening is that actually a thin film of water is going onto that surface because only the surface interaction is really doing anything. The inside is protected and the rest of the water is protected. So you're having this kind of surface interaction where the atoms or the ions are being kind of pulled off and surrounded with water molecules. You see the surrounding by water molecules here? And then at some point you reach what's called a dynamic equilibrium, where not only is that happening, but the reverse is also happening. So the solute molecules, the ions, are also coming back together to form more sodium chloride. They're going out, coming back, going out, coming back. And equation-wise, this looks like this. At first, you see the sodium chloride just breaking up. But then at some point, this is going to reach what's called equilibrium,
which means both things are happening at the same time. It's balanced out, and you're getting the solid sodium chloride into sodium and chloride. You're also getting the sodium and chloride ions in solution to come back and form sodium chloride. So depending on the energetics of this interaction, that is which side is more stable, heating it up could push it one way, it could also push it the other way. So there are some exceptions to where actually heating up a solution will make it go back the other way and bring it out of, and go more toward the solute. And one example of that, come on, is not here, of course. One example of that is gases. That if gases, when you have a higher temperature, you actually decrease the solubility because the gases can more easily escape from solution. So that's like that flat pop thing. If you keep pop in the fridge, even if it's open, it's going to go flat a lot slower than if you leave it out on a hot day, right? Have you seen that, or you keep ice in it or something like that? So here's a graph of some of how solubility changes with temperature. You see some cases it's a big change, like potassium nitrate. As you increase the temperature, this green line, the solubility goes way up, becomes way more soluble. But something like sodium chloride, it only really becomes slightly more soluble this way. And then there are some really unusual stuff like sodium sulfate. Solubility actually goes down as the temperature increases, which is not the norm. Because of this idea of dynamic equilibrium, that in that case, adding more energy to the system actually pushes the equilibrium in the other direction and forms more solid, makes the solid form more easily. All right, so we know about vapor pressure of liquids. What do you think about the vapor pressure of solutions? So would a sodium chloride solution have a higher or lower vapor pressure than just water by itself? It says the answer, but see if you can figure it out by looking at it and reading it. Can we at least understand it? So what's happening in a sodium chloride solution? Let's look at these examples. On the left, we have pure water. And remember that vapor pressure is also a dynamic equilibrium, where molecules are escaping from the water, from the liquid water, to become water vapor. And then they're also going back down. So they're going back and forth and back and forth. When you introduce the solute, you reduce that rate of vaporization. So you're having fewer molecules escape because they're now interacting with the solute. You can think of the solute as being kind of a magnet that's holding some extra water molecules in. So they're not escaping as much. And if they're not escaping as much, now we have a new equilibrium reestablished where some of those vapor particles come back down into the water to equal out that chemistry, equal out the two sides of the reaction. So when those vapor molecules come back down, you've reestablished equilibrium, but now you have fewer molecules in the gas phase. So that's a net reduction in the vapor pressure. Now that's all kind of, it's good to think about it in that way, but as kind of a shorthand, if you think about that solute as magnets analogy, it's not really what's happening, of course, but that idea that the solute is drawing more molecules from the vapor down into the liquid will at least let you get the trend right. As you dissolve more stuff in the liquid, you'll decrease the vapor pressure, so the solvent molecules will go down into the liquid more. And then I don't think we have to get into ideality and non-ideality. But let's look at what we call colligative properties, which is how these things affect boiling points and freezing points. Here's an example of where we use this molality. The reason being because we're looking at changes in temperature. And as we talked about, since volume changes, since density changes based on temperature, we have to use a mass-based measurement to talk about this. To predict a change in boiling point, again, there's a way we can calculate this with a specific constant. But what I'm more interested in is can you explain the cause of it? So boiling point elevation says that when we dissolve something like sodium chloride, when we dissolve a solute in a solvent, we raise the boiling point of the solvent. It goes up. If water boils at 100 degrees, that means that water with salt in it is going to boil above 100 degrees. Why do you think that is? Let's see if we can come up with a chemistry-based explanation as to why this boiling point would be elevated.
By adding more of the compound,
Yeah.
the vapor pressure is reduced.
Right.
And if the vapor pressure is reduced, in order to make it boil, the vapor pressure has to be the atmospheric pressure.
Okay.
So you have to increase the vapor pressure even more than you are.
Okay. What do you think about that? Hear that? So if the solute decreases the vapor pressure, that means that you need more energy now to reach to get the vapor pressure to reach the atmospheric pressure. Does that seem right? Does that seem reasonable? Yeah, I think so. It's that same kind of effect, that same idea of, again, that's a better explanation, but we can think of it kind of as this magnet that's holding things in solution. It's going to take more energy to get more of those molecules to give them the energy to escape the liquid matrix of the water and end up in the vapor phase on top. And you can calculate these with these various equations. I'm not sure that's totally necessary. It also affects the boiling point. And since I don't have the picture in here, I don't know why my notes are not great for this chapter. I must have forgotten to put a bunch of stuff in there. But we can look at a phase diagram and kind of sum all this up now that we know about phase diagrams. You can see here the pure solvent is kind of in blue, or in the inside. It's labeled pure solvent. And then the solution is these new red lines. So you can see what happens to the solution at a particular pressure, like 1 atmosphere. The freezing point goes down, and the boiling point goes up. So you end up with a bigger range between the boiling point and the freezing point, kind of expanding on both sides. The freezing point depression is, make sure they don't really talk about it in here, is a slightly different effect. And we can't talk about it purely in terms of intermolecular forces like we can with the boiling point. It has to do more with interference of making that solvent matrix and something called entropy. But we'll get into that in a little bit when we talk about cooling. Let's just look at this. This is an effect that you should just be aware of. Can anybody give you an example of when you use an effect like this? Where you see these things in use in life? When do you perhaps add things to lower or raise a boiling point or a freezing point in a particular way? Yeah?
It's icy roads.
So salt for icy roads, we're going to talk about that. That's related to this for sure. It's a little different because the ice is already there. So the fact that the salt melts the ice is a slightly different thing. But yes, that if another way we could say that is when the roads are wet, after they've melted, the salt prevents them from refreezing. Right. But that's also why we'll see at really low temperatures, like when we have those crazy winter days that go down to -17 or whatever, the ice doesn't really work. The water freezes back because it depresses the freezing point, but only so much. That's one example. What's another example? We all seen this sort of thing at work? I guess there's not really that many examples of this. We've talked about this before, but antifreeze in your car is another example. Antifreeze does both of these things.
the solution between water and ethylene glycol lowers the freezing point so that it doesn't freeze in winter, hence antifreeze, but it also raises the boiling point so your car doesn't overheat. We talked about how sometimes if you just put water in your radiator or when the ethylene glycol breaks down, sometimes what will happen is your engine will get too hot and then it'll like steam, and you might see people like pulled over on the highway or something with steam coming out of their engine compartment. And that's what's happened, that the antifreeze is broken down. In fact, when you check your check your fluid levels and stuff like that, you can check the specific gravity of your antifreeze, make sure there's enough ethylene glycol in there still that it hasn't broken down. Modern formulations don't break down as much, but that still should get flushed and changed every so often so that you're not in danger for that. And that's an example of where that might happen. All right. I guess we'll finish up with this. Osmotic pressure, and then then I just want to mention one other effect, and then that'll be it for today. So osmotic pressure is an important aspect, and we're actually going to hear about this on Wednesday in the presentations, because somebody, you guys, right, are doing dialysis? Yeah. So they'll talk a little bit about osmotic pressure and these kinds of semi-permeable membranes. Does anybody know what osmosis is? What's osmosis? Oh, it says right there. Shoot. I went to. Guys, hide that better. All right. The flow of solvent into the solution through a semi-permeable membrane. But specifically, osmosis generally refers to water. That a semi-permeable membrane means that it can pass water molecules as well as other things, as we'll hear about, but cannot pass large colloidal particles. What type of semi-permeable membrane do we most care about when we talk about osmosis usually? Why this very specific type of membrane? Why do we bother talking about this specific type of membrane? Anybody know what is made of this type of a membrane that is important? Cells, yeah. So a cell membrane is this type of membrane. And so osmosis is very important in how it predicts what's happening to the cells in our bodies. The idea here then is if you have some solution over here, so there's water molecules and solute particles. That should say solute, not solvent. You end up having water getting pushed through this membrane to try to equalize the concentration. So that actually creates a pressure that can push against this membrane. You see how the water levels are different here? The water level rises on this side and falls on this side with nothing else but a concentration gradient. So just by having a higher concentration on one side than the other, you can create a pressure that can actually do work and actually push up there because of the associated effects there. Now, there's a lot of interesting reasons behind this, get into entropy and stuff like that. In a cell membrane, this is important because if the concentration inside the cell is different from the concentration outside the cell, like in a bloodstream, then you're going to have water passing either into or out of the cell, and that can potentially damage the cells. It can also affect things like blood volume. So when you look at, and again, I'm just going to use the pictures in the book because I don't want to draw stuff. Again, we'll go back to our IV bag here. We've seen 0.9% sodium chloride as kind of a standard solution. It kind of seems like a random concentration, but that's what we call an isotonic solution, meaning that the ionic concentration of that 0.9% sodium chloride is going to be equal to the concentration inside the cell. And so you won't change you won't flow water into or out of the cell with having too much or too little solute. If you do have that situation, you can have this kind of thing happen. So here's your normal red blood cells, and they use slightly different words in the book. They use isosmotic, hyperosmotic, and hyposmotic, which is awkward words, but probably a little more accurate. But the common terms are isotonic, hypertonic, and hypotonic. So you have your normal red blood cells. If the concentration in the blood is higher, you will draw the water out of the cells, and they'll kind of shrivel up and make these things, these shriveled red blood cells, which is called crenation. And then if the solution in the blood is less concentrated, water will flow into the cells, which swells them, and they can actually burst. So that one part of that is just to kind of like be careful to not damage the blood cells when they're doing this. But sometimes, especially in emergency type situations, you want, for instance, sometimes you want a hyperosmotic solution because you'll quickly draw fluid out into the blood and you'll increase blood volume rapidly. Now you have to be really, really careful with that because you can seriously do some damage. But if somebody has shock or something like that and you need to get a lot of fluid going like really fast, that's one technique that doctors can sometimes use for that. Same with this. If there's too much fluid, you can kind of say, hey, blood cells, why don't you take some of this fluid for a little bit while we figure this out? But you have to be really careful that you don't cause problems that way. So that's one way that osmosis works. All right. So that said, let's talk about one interesting application of this that I thought was interesting anyway, is drinks. Weird heading for a lesson, I guess, but I assume you've all had some drinks, water, coffee, whatever. What?
Never.
You've never tasted a liquid? That is probably not good. You should see somebody about that. But the type of drinks I want to talk about right now are alcoholic drinks. Now I know some of you are too young to have tried alcoholic drinks, but when you get older, you can taste them and you can see what you think about them. Specifically, I want to, and this is weird that I'm being so specific here, but I want to talk about something called mixed drinks or cocktails. Does anybody know this? Has anybody ever worked at a bar as a bartender or anything like that? Served drinks, made drinks? Okay, that's fine. Well, so we're going to talk a little bit about how this works because there's really some interesting chemistry at work. Has anybody ever seen somebody make a drink, like mix a drink at a bar? Yeah, so what are they doing?
Shaking stuff up and throwing it.
Shaking it up and throwing it in the air, yeah. Some of that is really important to the chemistry. The throwing it in the air, maybe not so much. But let's kind of talk about what this is. If you haven't seen it or if you haven't done it, you're usually going to take some kind of alcoholic drink, usually a strong alcoholic drink, so something that is 40% by volume. So when you see volume calculations that are usually listed on alcohol bottles, that's a volume to volume concentration. So volume of ethanol per volume of solution. You'll often see that written in something called proof. Have you seen that on the things like 80? It's double the volume concentration. So if you see something that's 80 proof, that's a 40% concentration. And so your standard kind of base liquors that have 40% by volume. Has anybody ever heard of any? You know any? Do you want to give me one? Never heard? No. Anybody know what alcohols have 40%? Yeah. Vodka would be one. Any more? No. But I was just curious if anybody did. Yeah, I should probably. These kinds of things, so etc. Vodka, rum, whiskey, tequila. The importance is the percentage, that this has a relatively high amount of alcohol. And then you're also going to generally put in some kind of sweetener. So sugar, or usually sugar that's been dissolved into a syrup, just because it dissolves more easily. And then some kind of juice, usually a citrus juice of some sort. So this is kind of a recipe for these types of drinks. And you take those things and you put them together with ice, a lot of ice. And then as you stir them together with ice, or you shake it in this thing with ice. And anybody know why you do that? Why is that? Is it just for show? Or does it change something about the drink? It changes something. Anybody want to guess what would change? What's the difference between drinking that drink before it's shaken or stirred with ice and after? There's two important things that have changed. Cold, right. So part of that is going to be for chilling, that it's going to chill the drink. And that's really part of what's interesting here. We'll talk about why and what's special about that chilling. But what's the other part? What else happens when you shake it with that ice? So yeah, it's mixed it all together, right? I guess that's there too. But even if you mixed it before you added the ice, there's still another change. What causes the chilling? What causes it to get colder? I mean, the ice does, but how? What does the ice do to make it get colder? It melts. So the other part of this then is dilution. Usually, when doing this, these things are diluted about 50%. So if you started with, let's say standard would be about 100 milliliters of ingredients. When you shake it with ice, you'd end up with 150 milliliters drink at the end after it was strained out because of the extra dilution. But what's really interesting to me anyway is this chilling. Does anybody know, probably not based on previous answers, but what would you guess is the temperature of that drink after it's shaken with ice? What do you think is the serving temperature of this drink that's shaken up with ice? What do you think is the coldest that it could be? Yeah, so like 32 Fahrenheit. Why do you think that? Because that's the freezing point of water? It's actually not. I mean, it is the freezing point of water. But the serving of these drinks is actually much colder than that. Actually, you want to serve these things around, I don't remember the exact, but I want to say it's around 20. All right, so you're talking about something that is being served colder than ice, and sometimes all the way down to 10 or less, I believe. So that, to me, is the really interesting chemistry question here. You take room temperature alcohol and sugar and juice. You mix it with ice at freezing temperature. You shake it up, and you have something that is lower than the freezing temperature. So what's going on there? Let's think about it this way. If you did the same thing, so I would do this as a demonstration, but I think we're not allowed to do that. I think if I ever just brought in like some bottles of alcohol or something. But if you do the same thing with just water, with those ice cubes in it, you shake the water, then you'd be right. Right? You shake something up with ice, you shake water up with ice cubes, and your temperature that it ends up as, the coldest you could possibly get it, is 32. So what's different here? Yeah.
As the water dissolves, the alcohol lowers the freezing point of the water.
So that's part of it, that the alcohol and the sugar actually involved here, which is a significant percentage. You're talking about 40% ethanol molecules, and then you've got the sugar, which is about usually a 50% by mass sugar syrup. So you have a lot of stuff here that is not water. And that water mixing with the ice lowers that freezing point. But that doesn't really explain the chilling. That just kind of explains why it doesn't refreeze. So the picture is actually a little bit more complicated than that. If we look at the surface of an ice cube, as best I can draw it, there's our ice cube. At the surface of an ice cube is an interface between liquid and solid water. So you take an ice cube right out of the freezer, it is solid, right? But if you let it sit for a minute, it's going to kind of get shiny as the water layer forms on the surface. So you have a slight layer of liquid water on the surface. When you then put that into a container that has sucrose molecules and ethanol, those molecules will mix with that liquid water that's on the surface of the ice. And that mixing then draws more water out to try to create that equilibrium. So we talked a little bit about that in terms of the vapor pressure, where if you change this one, you kind of change this interaction, other stuff comes out to balance it back out again. The key thing that's going on here is something called entropy, which is a measure of disorder. So you want to, by putting these other molecules in that liquid, you increase the disorder there, and that leads to more melting. So essentially you are pulling out that heat of fusion from the solution and putting it into the ice. And so that allows you to access temperatures that are lower than the ice itself. And that's really what's happening here. Do you have a question about that? Sorry, I thought I saw it at hand. No? Okay. So that's how you can access these lower temperatures. The same technique is at work when you make ice cream the old-fashioned way. Has anybody ever done that with the big bucket? You like churn around with ice? No? Okay. Well, if you get these old ice cream makers, you put your ice cream mix in the middle, and then you put a bunch of ice on the outside, and then you throw salt in it. And it's the same concept at work. And this is also the road salt thing that's going on. Adding the salt to it draws the water out into this layer to try to maintain that equilibrium. And in doing so, there's an energy change. And so you would draw the energy out of the ice cream mixture, which causes the ice cream to freeze quickly. You draw the energy out of the drink solution, causing the drink to cool much more quickly. And so there are a lot of bartenders and people who work in this that now shaking and stirring with appropriate technique is used so you can reproducibly and consistently access the same temperature, because certain drinks they'll want at a particular temperature versus another one. So they'll balance their stirring or their shaking to make sure that you're always getting that appropriate temperature. Yeah. And so that's really what's going on here. So that's an example of these kinds of properties that work. Questions about that? All right, should we call it there, or do you want to do some, or we could do some molality calculations or something if you want. So tomorrow, I mean, you're welcome to stick around if you want to work on some practice or whatever. Tomorrow, we'll have our quiz first thing, and the quiz will be on not what we talked about today, but stuff from last week. So just the molecular geometry, polarity, that kind of stuff. Then the rest of the day, I'll bring in a bunch of multiple choice questions like you might see on the exam. We'll go through, we'll practice. This is also the time for you to bring your questions, because on Wednesday we have the projects. We may not have time for any review or questions for the final. So bring your stuff tomorrow.